Hello students, good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are revising SHM and this is going to be third lecture of SHM. In this lecture we will cover angular SHM and some part of SHM which is exclusive to JEE mains like damped oscillation and forced oscillation. So without losing any further time, let me share my screen with you guys. So here we go. So angular SHM we are going to talk about right now. So we have already learned about linear SHM. So for linear SHM you understand this differential equation when d2x by dt square plus omega square x was established, okay, and the solution to this was nothing but x is equal to some a sine omega t plus some phi naught, okay, where omega used to be root under k by m over here, okay. So for angular SHM, similarly we can write the differential equation would be d2 theta by dt square plus omega square theta, okay, is equal to 0. So that will give us theta is equal to theta naught into sine omega t plus some phi naught, where omega would be something known as root under k by I. Okay, so here omega will be the angular frequency of SHM. So let's have some example of angular SHM. The best example of angular SHM is physical pendulum. Okay. So here you see, let's say we have a rigid body and let's say it is suspended from point P and it is, let's say, in vertical plane, okay, and it is hanging under the influence of gravity. So let's draw a vertical line passing through this point of suspension. So in a stable equilibrium position, its center of gravity and C and P here will be lying on a vertical line. Okay, so right now this is in equilibrium position because the weight will be effectively acting in downward direction, effectively passing through C. Okay, so mg here, as you can see, line of this force is passing through P, so it will not produce any torque. Okay, so it is right now in stable equilibrium position. But what if we displace it slightly, give some angular displacement theta in this direction, and let's say that is small, so small angular displacement theta that is tending to 0 over here. So then you should realize the center of gravity will come somewhere over here, and this mg, now you should realize, like, mg will, you can resolve it in two components, that would be mg sine theta and this component would be mg cos theta. Okay, so this mg sine theta over here, mg sine theta over here would be producing uh, restoring torque over here, right? So can we write the equation of torque? Definitely we can. So equation of torque would be tau is equal to, that you can say that is nothing but the force is mg sine theta. Okay, and let's say the distance between C and P is, say, L. Okay, the distance between C and P is L. So the torque would be mg sine theta into L, you can say. Okay, and we will be having a negative sign because the direction of torque would be restoring. This would be the direction of torque over here. Okay, and torque here can be written as like I alpha, or that would be, I would be moment of inertia of this rigid body about an axis passing through this point P. So IP you can write, and this term would be nothing but d2 theta by dt square over here, or simply alpha you could have written, and that will be equal to minus mgl. And since theta is small, sine theta will be approximately equal to theta, so we can use that approximation over here. Okay, so you clearly see that d2 theta by dt square is equal to minus mgl upon ip times theta over here. So when you will be comparing it with minus omega square theta, clearly you can see that omega is nothing but root under mgl upon ip. So time period of oscillation simply would be 2 pi root under ip by mgl. You should realize, like, what is this term ip? Ip is nothing but the moment of inertia uh, of this rigid body about the axis of fixed axis of rotation, you can say. And this L is nothing but the distance between the point of suspension or axis from the center of gravity. Okay, the perpendicular distance of center of gravity from the axis of rotation, you should realize. Okay, so if we are able to find out these two quantities, no matter what is the shape of physical pendulum, we will be able to get its time period. For example, let's take one case here. Say we have a solid hemisphere. Say this is a solid hemisphere of mass m and radius r, and it is say suspended by this point. So say this is axis of rotation. This is axis of rotation. Okay, so this point P, this right now we have drawn it in stable equilibrium position. If we displace it slightly, it will be obviously experiencing a restoring torque. Okay, and when we release from that position, it will be executing angular SHM, and we wish to find out the time period of that angular SHM. Okay, so we know the time period relation for a physical pendulum is nothing but 2 pi root under IP upon MGL. So let's try to figure out what IP would be here and what L would be here. Okay, so you should realize the center of mass of a solid hemisphere will lie somewhere over here. Let's say this is O, and this is center of gravity or center of mass in that case, and this point is P. So this distance, you should realize, is nothing but 3r by 8. So this distance would be nothing but 5r by 8 clearly, and that basically is L, because that is the distance between C and P over here. Okay, so this L thing we have found out, and now we are looking to find out the value of IP, that is the moment of inertia of this solid hemisphere about an axis passing through point P over here. So you should realize, first of all, like, moment of inertia about point O, okay, or axis like parallel to P about axis passing through O over here, something like this. So that is going to be um, for solid sphere, it is 2 by 5 mr square. So for hemisphere also, due to the symmetrical mass distribution, IO would be nothing but 2 by 5 mr square over here. So you should realize that IC, first of all, IC would be nothing but, using parallel axis theorem, that would be nothing but I naught minus m into, like, the distance between them is 3r by 8 whole square. Okay, so like that is the thing, and then you can find out ip, and ip would be nothing but ic plus m into 5r by 8 whole square, and this is basically using parallel axis theorem. So when we will substituting these values, ip will mr square you can take common, and inside the bracket you will be having 2 by 5 minus 9 by 64 and plus 25 by 64 over here, and solving this you will be able to get 13 by 20 mr square over here. So ip we have also got, so we can find out t now. So that is 2 pi root under ip, that is 13 by 20 mr square into mgl, and L is nothing but 5r by 8 over here. So simplifying that, you will be getting 2 pi root under 26r by 25g over here. So that is one of the problem. Okay, let's look at some other example of angular SHM. Okay, this was one case of physical pendulum. You can have many problems of that nature, like for example different type of bodies suspended with different points. Okay, and you can find out the time period, etc. Okay, so that was one model. Another model let's look at is this. Say we have a rigid rod. Okay, rigid uniform rod, let's say, in horizontal plane. Okay, and say in that plane it is hinged at this point p, and its mass, let's say, is m and l, and it is connected with some springs here and there. Let's say one spring of spring constant k2 is here, and another spring of spring constant k1 is here. Let's say this is the midpoint over here, this is the extreme, let's say a. Okay, so this is the situation. This whole thing is in horizontal plane. Okay, and if we rotate, give it a small angular displacement to this rod and release it, we have to prove that its motion would be, subsequent motion would be angular SHM, and we have to find out the time period of it. So how can we do that question? So in order to do that, first of all, we would be give small angular displacement theta, okay, about this axis passing through point p. So you should realize this point effectively will advance by l by 2. This length here is l by 2, you realize. Okay, so L by 2, this point C will advance by L by 2 times theta. So that is why the stretching in this K1 spring, you should realize, will be equal to L by 2 times theta. Okay, and obviously if it is, this spring is stretched, so this will exert a restoring force in this direction, and its magnitude would be nothing but K1 into L by 2 times theta. Similarly, point A will move rightward, okay, approximately by L into theta. So this spring K2 will be compressed by L times theta over here. So in that case, it will also exert a restoring force, and that will be equal to K2 times L theta over here. So that's the idea. So when we have displaced it slightly, we can see due to the presence of these two springs in horizontal plane, we are getting restoring force, and these restoring force will be producing restoring torque. So we can write the equation of motion, the equation of torque over here. So about point P we are writing, so we are looking for this expression, I alpha is equal to net torque over here. So I here is nothing but about point P, this is uniform rod, so its moment of inertia would be nothing but ml square by 3, and alpha we can write definitely, that is d2 theta by dt square over here, and tau, you should realize the restoring torque, so there would be a negative sign over here, and you can write it like the torque due to this force would be this force into this arm, so that would be nothing but k1 L by 2 theta into L by 2, so you can write it as L square by 4 like that. Okay, and the another torque would be K2 L theta into L, so that would be K2 L square theta, you can write. Okay, so this is the form we have got. Okay, so d2 theta by dt square we can definitely write, for example, you should realize this L square term will get cancelled both sides. Okay, and this will be 3. Okay, and in this bracket you will be having k1 plus 4 k2. k1 plus 4k2 you will be having, and in denominator you will be having by 4 by m over here, and theta will get out. Okay, so obviously this was the form we were looking for. Okay, so obviously the time period would be nothing but 2 pi root under 4m divided by 3 k1 plus 4 k2 etc. Okay, so this was one model. So this problem was in horizontal plane. Let's suspend this rod in vertical plane and attach to it some spring over here. Okay, so let's look at this question. For example, we have a rod, okay, and that is suspended by point P, and its mass is ml, and now this plane is a vertical plane, and let's say we have some spring over here, okay, of spring constant k. Okay, so if this rod is given small angular displacement, say its orientation has been changed to this, and let's say this is small angular displacement theta. So at this position, when the rod will be at this position over here, what restoring force it would be experiencing. Okay, so for example, this point here, this extreme point would be moved approximately by L times theta. So like this spring will be exerting a restoring force, okay, that would be K uh, into L times theta. That obviously that would be the cos component, but theta is since small, so cos theta would be tending to 1. So we are able to use that approximation over here. So that is KL theta. And another force, restoring force, you should understand, because this is lying in a vertical plane. So you should realize the weight effectively would be acting at center of gravity mg, and its restoring component would be nothing but mg sine theta over here. Mg sine theta, and theta is small, so you can simply write mg theta, right? So when we will be writing this equation, tau is equal to I alpha. Okay, so I here would be about this axis, that is nothing but ml square by 3 again, and alpha is nothing but d2 theta by dt square, and net torque over here would be restoring in nature, so that is why we will be putting a negative sign over here. And you should realize one of the torque will be due to the scale theta force, so that would be KL square theta, and the another restoring torque would be due to this component. So uh, mg theta into its arm would be L by 2 over here. So you should realize, so this would be the differential equation. And when we will be rearranging that, okay, d2 theta by dt square, we will get it as uh, that would be simply 3k by m. That would be the first term, and the second term would be nothing but 3g by 2l over here, and theta obviously we will be able to take out. So in that case, the time period here would be nothing but 2 pi root under, okay, uh, like 1 by this coefficient over here, so that would be nothing but 3k upon m plus 3g by 2l, right? So this is the time period. Okay, let's look at one another model in which we will be having rolling of a round body. We will be combining this angular SHM with rolling. So this here is the question. So for example, there is a, say, cylinder, say solid cylinder we are having, of mass m and radius r, let's say, and it is kept on a rough horizontal surface. Okay, and see, like this, the roughness of surface is such that like it is sufficient enough for pure rolling, right? And let's say let's connect several spring to this sphere over here. So this is one of the spring. Let's say its spring constant is K, and it is connected to the center. And let's another spring connected at topmost point. Let's say its spring constant is K2. Okay. So if we displace this cylinder slightly, we wish to establish that the subsequent motion will be SHM, and we wish to find out its time period over there. So you can write a equation of force and equation of torque about center of mass, okay, and eliminating variables, you will be able to get either equation of torque or equation of force. So it would be better to treat the motion, okay, as purely rotational motion. We can do that about an axis which would be instantaneous axis of rotation. Okay, so here in this case, you understand this point of contact would be nothing but instantaneous axis of rotation. Let's say that is P over here. So we can consider a pure rolling or purely rotational motion about this point P. And let's imagine, okay, like we have given a small angular displacement about this point P of theta, right? So in that case, imagine it to be the purely rotational motion about this point P. So in that case, this point will be moving further by r times theta. Okay, so this spring here will be elongated by r theta. So this will exert a restoring force that would be nothing but k1 times r theta. And similarly, this spring here will be compressed by 2r times theta. So that is why it will be exerting a restoring force that will be in this direction only, and that would be 2k2 into r times theta over here. So now we are ready to write the equation of torque here. So equation of torque, you should realize, okay, about point P, when I will be writing I alpha is equal to tau. So about point P, the moment of inertia of the solid cylinder would be nothing but 3 by 2 mr square, and alpha would be nothing but d2 theta by dt square over here, and torque here would be due to these two forces, and you should realize that would be nothing but minus k1 r square theta, okay, minus 4 k2 r square theta over here, right? So obviously we can rearrange this. So d2 theta upon dt square, we will be able to get that would be equal to minus, okay, that would be 2 times k1 plus 4 k2, because r will get cancelled anyway, and that divided by, you can write 3m over here into theta. So time period of this oscillation will be nothing but 2 pi root under 3m upon 2 k1 plus 4k2 here. Okay, so this was another model. Let's look at a few more models of angular SHM in which we will be having some rolling. Okay, so this is another famous problem I am taking. So let's say this here is a solid hemisphere of mass m and radius r, let's say, and that is kept on a rough horizontal surface. Okay, so here let's say this is center, this is the point of contact. Okay, and right now it is in stable equilibrium position. The surface is sufficiently rough for pure rolling. Okay, so if I displace it, if I disturb it slightly, this solid hemisphere, okay, so a subsequent motion would be SHM, we have to prove, and we want to also find out the time period of it. So let's disturb it slightly. Okay, so when this solid hemisphere will be disturbed slightly, okay, its orientation would be something like this, you should realize. Okay, okay, so that is say small angular displacement. Let's say this would be the vertical axis, and this is the axis of symmetry, you can say. So this angle here is very, very small. Let's say theta, that is the angular displacement over here. Okay, so in order to find out the time period over here, we wish to write the equation of restoring torque, and we wish to establish that it would be of form some minus k theta. So let's try to do that. So at this stage over here, okay, so what all forces are acting on this? So let's say there would be a normal here, and the center of gravity would be somewhere here. We already learned it, like this would be from this point O, this point is C, so this distance got to be 3r by 8, we realized already. So this would be mg. Okay, and it would be very good over here to write the equation of torque about the instantaneous axis of rotation. Instantaneous axis of rotation. So since that is pure rolling, the horizontal component of acceleration of this point will be equal to 0, and centripetal component would be negligible. Okay, so the acceleration of this point P is negligible over here, so it will about point P, like when we are writing the equation of torque, we do not have to consider any pseudo torque. Okay, so like if we write the equation of torque about point P, okay, so we need to write I alpha or IP alpha is equal to tau. So IP, you should realize, let's say this point is Q. So IP will be approximately equal to IQ. IP will be approximately equal to IQ. And we have just calculated that it would be equal to 13 by 20 mr square in the previous question. So like this term we know, so let's write it, that is 13 by 20 mr square into alpha would be nothing but d2 theta upon dt square. And restoring torque, you should realize, about point P, it would be only mg which would be producing torque, so that would be mg into its arm. You should realize this distance would be nothing but arm, which would be nothing but 3r by 8 into sine theta. So that would be minus mg into 3r by 8 into sine theta, and sine theta is very very small, so sine theta will be approximately equal to theta over here, and that is what we were looking for. Okay, this type of expression we were looking for. So hence proved that the motion would be SHM for small angular displacements. Okay, and when you will be rearranging that, you will be getting d2 theta upon dt square is equal to minus 15g by 26r over here into theta. So obviously the time period here would be 2 pi root under 26r by 15g. Okay, so that is the time period over here. Let's take one more example where we will be having some rolling. Okay, and that is also quite famous problem. So let's say we have a curvature over here, curved surface of radius of curvature, say this is some capital R, and here we have kept a let's say we have kept a um, solid cylinder, let's say solid cylinder of mass m and radius r, and this surface is also cylindrical curve. Okay, so uh, so right now here it is in stable equilibrium, you should realize. Okay, because the net force and net torque acting on this cylinder is equal to 0. So if it is displaced slightly, let's say for example from this position to this position here, okay, so its center of mass would be moving somewhere here. Okay, and we wish to find out what would be the time period of oscillation. So let's say this angle here is phi. Okay, and you should realize, for example, this sphere will be rotating about its own axis because it is rolling also. Okay, so let's say angular displacement of this ball, okay, due to rotation is say theta. So let's say, for example, this point is A over here. So this point will come somewhere here, right? So this angle here would be some theta, and you should realize this angle is phi. Okay. So for rolling, you should realize that this length, this arc length will be equal to this arc length over here. So this arc length, okay, can be written as r times phi, and this arc length over here, because the radius of a small ball is, let's say, small r, so that can be written as small r times theta plus phi over here. Okay, so that gives if phi we wish to write, so phi would be nothing but you can, let's solve it here. So phi would be nothing but r times theta upon capital R minus R. So that is one of the relationships. Okay, and now you should realize also that when it is at this position, okay, and we wish to write the equation of torque about, let's say, this point, because this point, it would be instantaneous axis of rotation. Okay, and the force that is acting, that will be producing torque, would be the component of weight, so that is mg. And you should realize its tangential component over here would be nothing but mg sine phi. So when we will be writing the equation of torque, tau is equal to I alpha. So I, you should realize about point P for the cylinder, that would be nothing but 3 by 2 m small r square, okay, into alpha would be here, you should realize that would be d2 theta by dt square, and that would be equal to restoring torque, you should realize that would be minus mg, and the force, the component of tangential component of force would be mg sine phi, you should write, and its arm is nothing but small r over here, and sine phi will approximately be equal to, you should realize, that will be equal to phi. Okay, and phi we have already got in terms of theta, so that would be nothing but minus mg, and if we substitute the value of phi, so that would be r square theta upon r minus r over here, right? So let's write it, that is 3 by 2 mr square into dt theta by d2 theta by dt square. So you should realize this m will get cancelled, and this r square will also get cancelled. So d2 theta by dt square here would be nothing but you can say 2g by 3 times capital R minus R into theta, and obviously there would be a negative sign over here, so obviously the time period of oscillation in this case would be 2 pi root under 3 times r minus r upon 2g. So that would be the time period of small oscillations. Okay, so we have looked at a sufficient number of problems, okay, for angular SHM. So now let's move on to one another thing, that is composition of SHM. Let's write the heading, composition of SHM. Okay, you should realize that a SHM is produced when a restoring force proportional to displacement acts on a particle. And if a particle is acted upon by two separate such forces, the resultant motion of particle is composition of two SHM. Okay, and the resultant motion will be SHM only if frequency of combining SHM is same. So let's look at that case. Let's say, for example, one SHM we know and another SHM we know, so the resultant motion would be nothing but the vector sum of both the SHM. So let's look at different cases. So first case that we will be looking at, if two SHM we are combining are along same direction. So say two SHM along same direction we are trying to combine. Okay, so let's take such example. Let's say one SHM is given by x1 is equal to a1 sine omega t, and x2 is, let's say, a2 sine omega t plus some phi, let's say. So you can see we have taken two SHM both are along x-axis, okay, and they are oscillating about same mean position, that is origin you can say, but with different amplitudes a1 and a2. And also you should notice I have taken their angular frequency to be same, but there is some phase difference between. Phase of first SHM is omega t, and the phase of the second SHM is omega t plus phi. So obviously the phase difference is phi over here. Okay, so the resultant SHM x would be nothing but x1 plus x2, and that would be nothing but the sum of these two quantities. And when you will be adding these two terms, you will be getting something like A will be resultant SHM, resultant amplitude you can say, and that would be sine omega t plus some theta over here. So the resultant SHM will be having same angular frequency and its amplitude would be A, and the expression of A, let me tell you, that would be same as you used to have in vectors. So that would be A1 square plus A2 square plus 2a1 a2 into cos phi, and that's a root under of it. Okay, and you should also realize this theta. Theta would be nothing but tan inverse a2 sin phi upon a1 plus a2 cos phi, that you can write over here. And also you should realize some special cases in this scenario, some special cases. Okay, like for example, first one, if theta is equal to or phi is equal to 0, so means there is no phase difference between these two. So the resultant SHM would be x simply will be equal to you can simply add them, so that would be nothing but a1 plus a2 sine omega t over here. The resultant amplitude A is going to be simply a1 plus a2 according to that relationship also, because phi is 0, so cos phi will be equal to 1. So this term over here is nothing but a1 plus a2 whole square, okay, uh, under root, so that is simply a1 plus a2. And you can have another special case, if phi is equal to pi over here, means they are out of phase, so then x would be nothing but you can say sine omega t plus pi would be minus sine omega t, so that will become a1 minus a2 into sine omega t. Here you can say resultant amplitude is nothing but a1 minus a2. So you should realize two SHM when we have added and when they had same angular frequency, as a result we are again getting SHM, okay, with same angular frequency, okay, but different phase and amplitude, and this amplitude and this phase will depend upon the initial phase difference or the phase difference between the two combining SHM. Okay, so that is one of the case. The second case let's look at is 2 SHM we are trying to combine along perpendicular directions. So 2 SHM along perpendicular directions. Okay, so let's take one such example. Say one is x is equal to a1 sine omega t, right? And the another, let's take say in y direction, which would be perpendicular to x-axis. So y is equal to, say, let's say a2 sine omega t plus some phi over here. So you should realize this is the expression of, like, this particle is or this is the SHM along x-axis you can say, and this is SHM along y-axis you should say. And when we will be combining these two motions, okay, the resultant motion, you should realize the resultant motion will be two-dimensional, will be in 2D you can say. Okay, so the particle will be moving in xy plane, you should realize. And if it is moving in xy plane, we would like to have its path, okay, or trajectory you can say. So we would like to eliminate t from these two relationship and get a relation between x and y directly. So what we can do over here, okay, so let's start. Let's say this is equation 1 and this is equation 2, and we can operate on equation 2. Let's say y is equal to at sine omega t plus 5 we have written. Okay, so a2, and this sine omega t plus 5 can be written as, we can expand it, so that is sine omega t into cos phi plus cos omega t into sine phi over here. So now we wish to eliminate omega t. So sine omega t's value, we can take it from the equation 1, and similarly cos omega t value we will also get. So this we will be having, or let's rearrange that a little bit. So left hand side, let's write it as y upon a2, and this term sine omega t over here would be nothing but x upon a1 into cos phi you can write, and the another term cos omega t obviously we can write since we have value of sine omega t, so that would be 1 minus x square by a1 square root under, that is the value of cos omega t into sine phi you can say. Okay, and what you can do, like you can take this side, like y by a2 minus x by a1 cos phi, okay, is equal to, and when you square to get rid of this root sign, so that would be 1 minus x square by a1 square into sine phi over here. And further simplifying that will give you a simple relationship. Let me tell you, that would be x square by a1 square plus y square by a2 square, okay, and minus 2xy into cos phi and upon a1 a2, and that will be equal to sine square phi. Okay, so this would be the equation of path of the these two combining SHM when we have combined two SHM which were in mutually perpendicular direction. So you should realize this is nothing but the equation of ellipse. This is nothing but the equation of a skewed ellipse, and you should also realize graphically. So since say like the looking at the expression of x, you can say like x will be varying between minus a1 to plus a1, and similarly y will be varying between minus a2 to plus a2. So you should realize this uh, the resultant motion will be constrained inside a rectangle. You should realize inside a rectangle. Okay, let's draw that rectangle here. Okay, defined by, let's say this is defined by these points. So let's say this is x is equal to plus a, and this is x is equal to minus a. So this is one line, this is another line, and say this is y is equal a1, let's say, and y is equal to a2 and y is equal to minus a2. So the ellipse we are looking at will be confined in this rectangle. So it would be something like this. Okay, so pardon for bad drawing. Anyway, like this would be looking like this. Okay, so and we can have some sub cases also. Okay, like for example, let's have one special case. Let's say case 1, when phi will be equal to 0. Okay, so when phi will be equal to 0, the equation which we were looking at, or simply if we substitute the value of phi in the equation we got earlier, or alternatively what we can do, since we have x is equal to a1 sine omega t and y will be equal to a2 sine omega t when phi is equal to 0. So you should clearly realize, like when we will be dividing these two equations, y by x would be simply a2 by a1 over here. Okay, so y is equal to a2 by a1 into x, and this is nothing but this equation of a straight line. So this is one of the special case. Means what I am trying to tell you over here, like the path of the particle would be a straight line with a positive slope, and the slope would be nothing but a2 by a1. And also you should realize like it would be oscillating along this line, okay, and this extreme is, let's say, x is equal to a1, and this is x is equal to minus a1, and similarly you can say this is nothing but y is equal to a2, and this thing is nothing but y is equal to minus a2. And similarly, another special case you can look into is special case 2. So when we will be having phi is equal to, let's say, pi, so in that case x will be equal to a1 sine omega t, and y would be nothing but a2 sine omega t plus pi. So that would be minus a2 sine omega t, and again you will be getting a straight line, but this time with negative slope. So you can say y is equal to minus a2 by a1 into sine omega t, and its graph would be something like this, okay. And obviously it is constrained between uh, a1 and minus a1 and a2 and minus a2 over here. So that is another special case. One another is interesting special case is special case 3. Let's write, okay, if phi is equal to pi by 2. So the equation which we have got is x is equal to 1 would be a1 sine omega t, and y would be a2 sine omega t plus pi by 2, which would be cos omega t, you should realize. So a2 cos omega t you can write over here, and squaring and adding both sides, so simply you will be getting an equation like x square by a1 square will be, or plus y square upon a2 square will be equal to 1 over here. So that is basically uh, a ellipse with x-axis as major axis and y-axis as minor axis over here. So this is one of the special case. Also you should realize if a1 is equal to a2, then this would be a circular path, okay. So these were some cases of combined composition of SHM, okay. So now let's look at some part of this chapter which is exclusive only for JEE mains, okay. And this part of the SHM is quite scoring once you are familiar with the ideas. So let's learn about the damped oscillation. Damped oscillation or damped SHM we will be looking at. Okay, so you should realize, like for SHM, we said that the differential equation we used to have is m d2x by dt square plus kx is equal to 0, and its solution obviously was nothing but x is equal to a cos some omega naught t plus phi, okay. This omega naught, that would be equal to root under k by m. We will name it as natural frequency of SHM. Natural frequency of SHM here, of natural frequency of this body, okay. So this is the case of the SHM when apart from the restoring force, no other net force was acting on the system. But see, like when the body is moving in a medium, obviously like some drag force, like the Stokes law, we have learned some drag force which would be directly proportional to its velocity and oppositely directed will be acting, okay. So that would be the real case scenario. So in case of damped oscillation, okay, so the net force which we are writing, like for example here when we will be writing mass times acceleration m times d2x by dt square, okay, that will be equal to some restoring force, that is nothing but minus kx, and apart from that there would be another force that would be directly proportional to its velocity, okay, and directly opposite to the velocity. So minus b times v would be its expression, and let me name this proportionality constant, that is known as damping coefficient, okay. Then damping coefficient over here, okay. So like when we will be writing it in a differential equation of x and t, so that would be m times d2x upon dt square plus kx, or rather First, let's write b time bv. So b times v is nothing but dx by dt and plus kx over here. So this would be the differential equation. And let me tell you, the solution to this differential equation will be x is equal to a naught into e to the power minus bt by 2m. Okay, this would be the amplitude term, and the oscillation term would be cos omega dash t plus phi over here. Okay, where the frequency of oscillation, or angular frequency of oscillation, will be omega dash will be equal to root under k by m minus b by 2m whole square. So this term here is coming due to the damping factor. Okay, so that would be that we will be having slightly changed angular frequency. But let me tell you one simple thing. For most of the cases, you will see that b by 2m uh, a whole square, or this term, would be much less than k by m. So this term would be approximately equal to root under k by m only, okay, which is same as the angular frequency of SHM. So the main thing is the influence of damping would be here, that the amplitude would become an exponentially decreasing function with respect to time. So let's look at this amplitude term more closely. So this amplitude term, you can clearly see that is nothing but a naught into e to the power minus bt upon 2m, where a naught is the initial amplitude, you should see, and it is exponentially decreasing term. So when we will be plotting its graph, okay, that is amplitude versus time over here. So its initial amplitude is a naught. Okay, so its graph will look something like this. And you should also realize that at regular time, let's say t half, its amplitude will be becoming half of the initial value, and so on. So if we wish to find out that after what time the amplitude will become half of its initial value, so that calculation is rather very simple. Okay, so you should realize at t is equal to t half, okay, a we want it to be equal to a naught by 2. So when we will be substituting these two values in this equation, we'll be getting a naught by 2 is equal to a naught into e to the power minus bt by 2m. And you are very familiar, in place of t, let's write t half, and you are very familiar with this expression, that would be ln 2 upon the coefficient of t. So coefficient of t over here is b upon 2m, you can write. Okay, so that would be the t half of the amplitude term, please understand. Okay, like this is the time after which the amplitude will become half of its initial value. Like if you will draw, like for example, x versus t graph, for example x versus t graph, the amplitude term will be forming an envelope. So this would be the envelope formed by the amplitude term. Okay, and the oscillation would be like inside this. So clearly you can see that amplitude is decreasing and slowly it will die over here. So that would be the graphical interpretation of oscillation in case of damped SHM. Okay, and let's also look at energy term a little bit, or mechanical energy of the system. Mechanical energy of the system. So in case of SHM, okay, we saw that the mechanical energy of the system was constant. So mechanical energy, instantaneous mechanical energy, we can write it as half ka square. And you should realize, but this amplitude is exponentially decreasing term, so that will become half k a naught square into e to the power minus bt by 2m square. So that will be e to the power minus bt by m over here. And if we say like this term is e naught, So E naught is into e to the power minus bt by m. So you should realize that mechanical energy of the system is also this time exponentially decreasing, okay, and it will vary exponentially. So this would be the curve again. So this is energy, mechanical energy versus time. So initial mechanical energy of oscillation was E naught, and it would be decreasing exponentially. And for t half of this, okay, like after how much time the energy of SHM will become half of its initial value. So you should realize ln 2 upon the coefficient of t, so that is b upon m over here. So that would be the t half for the energy term. Please notice t half for the energy term and t half for the amplitude term are not same over here, right? So this was a little bit about damped oscillation, and let's also learn a little bit about the forced oscillation over here. Forced oscillation. Okay, in order to take care of the damping, since energy is leaking from the system due to damping, we need to do some external work on the system to keep the system oscillating, right? With the same amplitude. Okay, in order to do that, we need to apply some external force. So the net force we will be able to write in this case of forced oscillation, that would be restoring force was already acting, and there was damping already, that was minus bv. Okay, and apart from that, we need to apply some driving force, driving periodic force, and that expression would look something like f naught into cos omega t, right? Where omega, you should understand, omega here is driving frequency, that is driving frequency over here, right? So so this would be the equation of force, and when we will be writing this in differential form, f, we can write it as m times d2x by dt square over here, and this bv term would be b times dx by dt, and this plus kx over here, and that will no longer be equal to 0 right now, and that will be equal to f naught into cos omega t. Okay, and let me tell you, like, its solution would be like when we have applied this external periodic driving force, its solution would look something like this, that x is equal to a cos omega t plus phi over here. So now you should realize this, some amplitude we have written which is not a function of time, that is a constant over here. And let me give you the value of a without derivation. Like the value of a will be simply equal to f naught upon m upon omega square minus omega naught square whole square plus b omega by m whole square. So obviously this amplitude term is depending upon the value of f naught. Okay, so f naught, it is depending upon, this drive this you can say this is this term was named as, we have already named it as damping coefficient, right? So it will also depend upon damping coefficient, and it will depend upon the angular frequency, most of all the angular frequency of the driving force. So let's explore this function a little bit, and let's try to have a graph between a and omega. Okay, between a and omega. Obviously it is, a is also depending upon b also. Okay, for a given constant force f naught, how will it look like? So let's try to plot it, and this graph will look something like, it will start from some point over here, that would be nothing but f naught by m omega, and this term will first increase when we will be increasing the frequency, and then it will begin to decrease over here, and at a very large angular frequency omega, the amplitude will become 0. So we basically are interested in this peak. Okay, so looking at this relationship over here, right? Looking at this relationship right over here, you should realize, Okay, like this peak will occur when omega is equal to omega naught. Okay, the amplitude would be maximum when omega is equal to omega naught. So this term will become 0, and only we will be having this term over here. Omega naught, let me tell you, that was nothing but root under k by m, which was nothing but the angular frequency of that system. Okay, so this is the condition of resonance. That is the condition of resonance. So obviously you should realize that omega is equal to omega naught. This term a, the peak value of a, you just have to substitute it over here, or you can write a max. So that would be f naught upon m. Okay, and you can substitute the value of omega naught over here. So that would be nothing but b omega naught upon m over here. Okay, so that is the idea. M and m will get cancelled, so that is a maximum. And also you should realize, like, this curve has been drawn at a given value of b. If we change the value of b, let's say we decrease the value of b, if we decrease the value of b, let's look at the dependency on b. So for example, we will be looking at this peak. What will happen to the peak? So at omega is equal to omega naught, we have already seen that a is nothing but f naught upon b omega naught over here. So a is inversely proportional to b. Okay, so if b is smaller, okay, a will be large, or maximum amplitude rather you say, a max would be large, and if b is large, a max would be small. So for example, for different b, we can draw this curve. Let's say this is b1 for b1, this is for b2, and let's say this is for say some b3, you say. So you should realize, see, in the case of the third curve, the peak is maximum. You should realize a maximum 3 is greater than a maximum 2 is greater than a maximum 1. So you can clearly say that the b3 will be less than b2, would be less than b1, etc. So this was a little bit about forced oscillation, and our time is up. So that's it for today. In tomorrow's class, we will be discussing about unit, dimension, and measurement and error analysis, etc. And the last class will be about the vernier caliper and screw gauge. So that's it for today. Thank you.